Hello, Dr. Tardos.
Hi.
Yeah, thank you again for giving a talk at our seminar series. I'll just begin by giving an intro and then we can go into the
Sure.
talk. Yeah, thank you. Oh, hi, everyone. Welcome back to the DDLC seminar series. This is Nishant, and it's a pleasure to introduce today's speaker, Professor Tardos. And she is with the Computer Science Department at Cornell University. And today's talk is going to be about learning and strategic QA. And a little bio about Dr. Tardos. She did her diploma and PhD in Athos University in Budapest, Hungary, and she joined Cornell in 1989 and served as the chair of the Computer Science Department from 2006 to 2010. And she's been elected to the National Academy of Engineering, National Academy of Sciences, and the American Academy of Arts and Sciences, and is an external member of the Hungarian Academy of Sciences, and is also a recipient of a number of fellowships and awards, including the IEEE John von Neumann Medal, the Packard Fellowship, the Godel Prize, the Danzig Prize, and the Fulkerson Prize. She served as the editor-in-chief of SciAm, Journal of Computing from 2004 to 2009, and is currently editor-in-chief of the Journal of ACM. And she also serves as editor in some of the journals, including Theory of Computing and Combinatorica. Without further ado, I'll let Dr. Tardos take on the talk. Yes, we can start now, Dr. Tardos.
I will. Thank you so much for the nice introduction. And I guess one thing I have to correct, I'm no longer editor-in-chief in Journal Combinatory Journal of ACM that ended, actually, I don't know, 4 or 5 years ago. I don't remember.
Okay.
Am I sharing my screen okay?
I'm not able to see your
Can't
screen.
see the screen. I don't quite know how to do this then. It's just sharing. And then when I do this, it's not actually happening. It's sharing something. It's not
Yeah,
sharing.
I can. Yeah, I can see it now.
It's my screen, I hope.
Yes.
True
I can
fact?
see the slides. Yes.
Oh, good. Okay. So let me actually move this out of the way. Good. Okay. So I guess the title is Learning in Strategic Queuing Systems, but I guess I want to start from, my motivation for, where I'm coming or why I'm doing this. And I certainly view queuing system as a very interesting application, but I was more interested in the learning in strategic settings in general. Queuing system is one of those settings. So I guess, I've been working on games and strategic interactions, and I guess what is catchily called the price of energy, the worst case gap between social welfare in Nash equilibrium compared to a centrally designed optimum. I guess in this sort of more recent version of agenda, I consider games that are repeated interactions where participants might want to use some sort of learning method to figure out, how to best respond or how to behave in a game or an interaction. There are a couple of natural questions here, which we all going to vaguely touch on. Certainly have to define what I mean by learning. The interesting question is what form of learning ensures that something reasonable is happening, and I guess what we can say about outcomes as people learn. For applications, I think my ever favorite application is traffic routing, and maybe that's closest to what maybe civil engineers need to usually think about. I guess the simplest model here is that that the speed at which traffic can proceed has a function of congestion, and that, of course, more congestion causes more delay. And in this model, I guess at this point, maybe 25 years ago, something's wrong with my video. Is that true?
Yes, it's your screen.
The screen
Uh,
is,
the screen sharing is totally fine. It's your video feed that's being interrupted.
yeah, I don't know what to do about this. 1 second.
Yeah.
No, it's okay, right? But now I'm not sharing. Can't, oh, am I sharing?
Yes, I can see your screen, but am unable to get a smooth video of your
Mhm.
face, basically.
I see. I think usually what I have to do is turn this off and then on again. Yeah,
Yeah, it's fine now.
maybe that solved the problem. I have to still get back the shared screen. Okay. So this is a sort of a classical result at this point, that in this very simple network routing game, if compare a Nash equilibrium with some traffic rate between source sink pairs to a centrally designed optimum with double the traffic rate, then I guess the good news is that the Nash equilibrium with some rate R is no worse than the Nash equilibrium with double the traffic rate. And the way I want to think about it, though maybe that's not the classical definition of price of energy, is the one highlighted in this yellow thing, is that if we give enough resources to the system to even central, when well designed, can support twice as much traffic, then apparently the Nash equilibrium is not so bad. It's no worse than this system with the double traffic rate. Again, the classical definition was just comparing, social optimum to Nash, and that unfortunately, even in this very simple game, can be very bad. But apparently, there is a increased set of resources. One can guarantee that life is a little better. I know in car routing and civil engineering, this increased set of resources does sound scary, and I don't know who can build twice as many highways. But in the packet routing and the internet, that's literally what's happening. They're just building enough capacity so packets can go through easily. And I guess maybe it's the other criticism I sometimes get, that there is this factor of 2 gap here, and how come I'm happy with a price we had paid for the good traffic that's having to build twice as much even on fiber on packet routing. Good point. It would be nicer if it was a smaller number, but as compared to something, what's happening here? Something horrible that can happen, such as what's usually called the price of energy, where I guess in some other simple example, well known under the tragedy of the commons name, one can, lose all welfare, not just a factor of 2 price, but a factor of, something, the number of users or some other things. Since this 2002 paper, there's like a huge literature that grew up around trying to do this, and there are lots of beautiful works, both in things like routing kind of things, and also in advertising auctions and auctions of any form, lots of them. And I'm not going to either list them or other than flashing up a slide that there are lots of works of this form. What I'm going to focus on is this learning aspect, because that's what I'm most interested in these days. And I guess to start with, one should ask, Nash equilibrium, that's a nice notion. And I guess, it's beautiful. And Nash got famous by proving that it always exists, which is nice. But it has a lot of troubles. And I guess maybe my favorite troubles are the one in red. There is insane amount of information needed for the players to know exactly how to reach a Nash. There is also more computer science trouble, that it's technically computationally hard to find a Nash equilibrium. So, why are we assuming that people find it? And here is something sort of better that I, Vanu proposed is very relevant in a lot of games, from car traffic routing actually to packet routing to queuing networks and all the other ones is this property. And here is a very simple theoretical or mathematical model. It's a repeated game. Iteration 1, people do something and something will happen. And then iteration 2, again, they do something, something will happen, and so on, all the later iterations. They keep repeating, playing, and something happens. I assume that, and this may be a slightly questionable assumption, that people care about, total cost or average cost. This is perfectly good in advertising auction. They indeed want to have enough value over the months. A bit less good in packet routing or traffic routing, where basically the assumption here is that they care about, on average, how fast they get to their destination or how fast the packets make it to the destination, and not worst case. But and the more interesting assumption is the last line here. I'm going to assume that players will try to behave the last line here, that trying to learn from data. So I have to be a bit more careful on defining what do I mean by learning from data, which I'll do next, but that's sort of the key question here. I should have said up front, if you have questions, especially as I more formally define the model next, clarifying what the model is, please ask, because I don't want to just keep talking and, losing a good chunk of the audience. So here is my model of what do I mean by learning while playing. So here is, again, the same picture. People started learning, and maybe initially they don't know what's going on, or maybe they do. But the idea is that by the time they played long enough, they hopefully have a better idea. So what applications is this reasonable? Applications where, and again, this is perfect for, I think, for packet routing. Maybe you can think about how good it is for other applications. Each step has very tiny value. So in even looking at packets or watching even a video on the internet, maybe you all know that losing one packet, actually the system is very well designed to recover from this. It's really no problem at all. They just resend the packet, you even don't notice that it happened. If you lose a lot of packets, then the video gets chunky and you can't watch it anymore. Same in advertising auction. If I paid for an ad that no one watched, that was unfortunate, but the whole thing cost like less than $1, usually even like pennies. And it doesn't matter. It's a multi-million-dollar industry, but it doesn't matter. So, packet routing is very well set up for losing a couple of packets. Ad auction is a multi-billion-dollar industry, but one ad is usually 10 cents, less than $1. So it doesn't matter. So learning while playing is okay, because a little bit of losses. You don't want to do insane amount of work ahead of time. Environment is changing, so what you learned ahead of time might not actually be valid. That's, learning while playing while learning, or learning while playing, is very reasonable. What do I hope for learning while playing? I'm hoping something very similar happens to what a Nash equilibrium would be. And here is my picture of what would happen if they magically actually find the Nash equilibrium of the game. Then they did something in the beginning, that's the learning phase here in black, and then eventually they somehow figured out what to do, and they keep repeating the very same action, which is the equilibrium behavior. Again, we don't expect this to happen, because remember, finding Nash equilibrium is computationally hard, so simple learning algorithm is not going to do it. But if they did it, then what would have is the following inequality, that this, whatever they reach to, ignoring the beginning, that the utility that player I gets from this vector A, that is A1 up to AN of what everyone does, is better than the utility this person could have gotten from any other action he can take. So this is a sort of standard game theory notation. Utility I for player I doing this new thing X, where A minus I is the funny notation, which is the A vector, where I skipped the I's coordinate and that got replaced by X. So this is player I doing something named X and everyone else following this strategy. And it's a Nash equilibrium if this is never better for this player who's changing his strategy. And that's a Nash equilibrium. Again, I don't expect them to reach this, but this is nicely called the no regret condition. That is, player I doesn't regret that they're playing this, repeatedly playing this strategy A, and they, if no one regrets it, that's called a Nash equilibrium. The only place I have data, so traffic routing, to be honest, I don't have data for, but only place I have data is adductions. And I'm certainly happy to report to you, or not happy, that absolutely not true that they reach such a Nash equilibrium. So this is a weak-worse data, actually from Bing, so Microsoft adductions. And all I can say, some people are somewhat stable here, like this blue line is pretty stable. Here wiggling, they add the bits a little bit, but some lines are very unstable. If I look at what's happening here, and especially if you happen to know that there are these sophisticated bidding tools available offered by various firms, then I'm thinking, yeah, they're running a learning algorithm, and they're running something probably called gradient descent. And this guy is sort of figuring out that bidding lower is better for him, and then I guess he overshot, and then his bids higher. The opposite version for the red guy who initially undershot, and then he's going under. This very much looks like gradient descent. So what would be something that I can assume they do? And here is the no regret condition that I like, which is totally identical to what was assumed for Nash, but instead of not assuming they reach something stable, but just that they learn something. And here is the assumption: do at least as well as a single strategy with hindsight. So I'm going to maybe elaborate on what this condition means, but let me first read it out. So you play it for some capital T time. I figure out what utility you got over all the time. So your player I, at time T, everyone does this AT option written here as a vector. This is your utility in the game. And what you're competing against is a single best thing with hindsight. So let me actually emphasize is that you can change your strategy as often as you want, and learning people do, as I showed you on the picture. But I'm hoping that this inequality is not only learnable, but actually beatable. You should be able to do better than this. So this is a sort of weak behavioral assumption. I added this little bit of error that over time T, you can have, something not growing linearly with T. So, the better learning algorithms do an error that's log T. Less good ones do an error that's root T, but I definitely want it less than T because, if I have time error proportional to the time, then you're constantly doing the wrong thing. If error doesn't grow with linearly with time, then hopefully you're getting better as time. On average, you're getting close to what this single strategy with hindsight would do. Those of you who know more game theory, I can point out that if people all do this, then there's a name for this and converges it to a form of correlated equilibrium. But if you don't know correlated equilibrium, don't worry about it. It is very much an inequality like the Nash equilibrium inequality, hence the very similar name. But you don't have to, there's no stability assumption. They're constantly doing different things. So to make people comfortable or not comfortable, again, this is inequality. So everyone does at least as much utility as they would have, or more or less, with a little bit of error, a single strategy with hindsight. On the positive side, this is doable. Like I don't need to know anything, no common knowledge. People just go in, there's standard algorithms that achieve this without any prior knowledge. In fact, these algorithms are even better than this And if the environment's a bit changing, they can even adjust and, change behavior, change with the environment. I love this, and I want to call this a behavioral assumption. I can name the algorithms. There is regret matching, there is multiplicative weight, there is hedge, there's standard algorithms that achieve this condition, but I don't want to make the assumption that anyone's running exactly my favorite algorithm, or for magic reason, I know what algorithm they're running, because I don't. I want to say that it's a behavioral assumption, and here is the sort of behavioral way to put this. If there is a consistently good strategy X that would have given you good value, then why the hell didn't you notice it? So here is sort of you going back to traffic routing. You're driving on, trying, experimenting with all kinds of things. You're in California because that's where driving is somehow a bigger issue. And somehow it turns out that had you always just chosen 101 to drive on, it would have been much better than what you're doing. Then somehow you didn't learn. There is a really good solution. It's called 101. It's even pretty simple. Why the hell don't you drive on 101? This is a beatable strategy. It could be that you know that 101 is actually really good, but when it rains, you should get off of 101 or something. Then you beat this because there's nothing that's consistently good. But if you don't even beat this or do as well as this, then I want to say that, hey, you didn't actually learn, weirdly enough. Again, simple algorithms use it. The algorithm is pretty natural, but I like it because I think it's a behavioral model that is easily usable in theory. It's an inequality. And I like the defense that this is a behavioral model. That is, if there's a good strategy that's sort of simple, one thing that you could do, please notice it, do at least as well, possibly do better. I can even offer you data from a 2015 paper that I had with, at the time, Cornell colleague Denis Nikifalov and a student, Vasily Sirkanis, that we had here. Again, this is the Bing Microsoft data. It's essentially true. Like a few advertisers have high regret. 30% of the advertisers we marked as zero regret, but what we mean is that these guys actually have negative regret. They're doing better than a fixed strategy with hindsight. And then the rest of them, a large percentage has within 10% or less than regret. This notion also did beautifully, and I guess my video is back to having problems.
Yeah.
I guess sorry. That must be, can kill the video, or maybe that's the way to go. Sorry. Can try it again. Put it back. Yeah, if I put it back, it comes back normal. Weird. And so this notion did beautifully in working for theory. It started by price of energy as a notion was introduced by Koutsopias and Papadimitriou in 1999. I guess about 10 years later, starting with a paper of Avrum Blum and a bunch of his students, and then beautifully summarized by Tim Ravgarden, they noticed that if instead of thinking about Nash equilibria, we think about everyone doing no-regret learning, then virtually all our proofs extend, and we can say the same things about no-regret learning. And in a paper, even another 6-7 years later, with two students here, we even generalized it for changing environments. And the conclusion that we all drew from this is that no regret is both natural, it's easy to justify as a behavioral assumption, and strong enough that if, all our beautiful work on price of energy for Nash equilibria extends. And because we only use some number of minutes of this talk so far, maybe you want to guess that my next slide will say, wait, not as good as can be. And here is my story for not as good as can be. there is a super strong assumption in all these works, and this is the strong assumption that every iteration you repeat a clean copy of the same game, totally new, with no carryover effect between runs, of course, other than what people learned from the previous runs. They're learning, but that's all that's happening. And that's not true in almost all the repeated games. So going back to the traffic routing, if I go with morning rush hour as my traffic model, so that's this part of that part of the slide over there. If I go with morning rush hour, it's reasonable. However bad Monday morning was, by Tuesday morning everyone went home. The roads are clear enough, and you can start again. Like I presume at 2 a.m. there or 4 a.m. there is no traffic jam, not even in California. But if I change the time scale, and on this slide, I changed it to packet traffic, but same applies on rush hour traffic. If I change the time scale to something much, much smaller, then it's not true. If there was a traffic jam at 2 p.m., then 2:05, hey, the same cars are still there. There is literally the same traffic jam sitting there. So there is carryover effect. Same on packet routing. If there's too many packets in a part of the system, and as you might know, packets get dropped at that point, and you have to resend them to recover the traffic, then of course these resent packets are causing new traffic jams and causing delays, so there is a carryover effect. So this is where our queuing system model will come in, and this is a work with Jason Gayatonde, who now is a postdoc at MIT, but was a student here at the time, when we did this work. So here's a super simple model of queuing systems, which is trying to model this. So packets arrive to the queues, they want to get to servers, and I'm going to assume that these queues, which is true in a big queuing system, have to do something simple to figure out what is the good server that they can use. The servers will try to serve the packets, but when things don't go well, then they're going to drop the packets and they're going to have to get resent. I'll tell you the exact model in a sec, but the kind of question I want to ask is what I tried to foreshadow in the beginning. Does price of energy stop bands still work when there is dependence between runs, as it is the case in this one? Is no regret learning a smart enough way to learn? And can we make a similar band than we had with the classical paper with Tim Rovgarden, that if I give the system enough capacity, then it's enough if everyone's just trying to learn. So that's the question I'm going to hopefully get to in the next 15, 20 minutes. So here is the actual model. There are queues and servers. Every queue will have a Bernoulli process in which new packets show up with probability lambda I every step. It's a property of the queues. Every server has a probability of serving packets. If you want these servers to be perfect, that's a good example to think about. I would, in part, we have this serving capacity, serving probability, because it supports our induction proof, but you can think of everyone is perfect. And I guess one restriction that's definitely true on queues in the internet is every iteration, every time step, every queue can send one packet to one server, and every server can process one packet. And I guess in this version, it just drops or returns the unsent packets. So that's the model. Or actually, to be honest, one more important question that arises here, if you can only serve only one packet and say on this server here, there are two packets arrived, then which one do you serve? And we do something that at turnout is actually implemented in modern queuing networks, try to give priority to all those packets. That is intuitively definitely helps, like gets the packets cleared. So if there are multiple packets arrive, they all have a variant of a timestamp, and we serve the other ones. Okay, so I want to know how bad is this model, and I guess what I'm going to do next is, in a couple of slides, try to help you understand how this system works and what would be needed if we fully coordinated, or what's basically needed, and then tell you a little bit about what we can prove and maybe even how we can prove it. So first of all, queuing theory 101. So suppose, just a very basic thing. One queue, one server. Lambda arrival rate, mu service rate. I guess maybe you won't be too surprised to hear that the length of queues waiting in the system becomes bounded, that is not infinitely long, if lambda is less than q. The direction when lambda bigger than q, that's obvious. If we have, packets arriving at every probability a half, but you can only serve them with probability a third, then obviously going to go behind. The other direction is not too hard either, and maybe the queuing theory's interesting version is what exactly happens when equal. I'm going to ignore this minor detail with the equal, but this is the result. It's actually, you need the strict inequality to keep the queues bounded. Okay, but we have multiple ones. So this would be sort of a baseline measure. Suppose I fully coordinate. There are multiple queues and multiple servers, and I fully coordinate between them. So, maybe in some iteration, I will tell this second queue that, sorry, don't send anything to this server or any place, because the other two guys sending, I'm giving them priority. And also tell the servers that, no, don't look at packet ages. Please, I tell you which one to pick. I can fully coordinate everything. How much do I need? For a fully coordinated measure, it's handy to get a mathematical notation straight to get them sorted by the abilities, because it's easier to talk about it that way. And our basic theorem is that in order for this to be servable, I need a very similar condition than what I needed for a single queue, lambda less than mu, except I need one for every level of k. So let's try to read this out. So it says for every k. So let's try with k equals 1. So k equals 1 says, look at the queue that has the most packets. You can only send to one place at a time. And even if I ignore everything else, what he needs, there should be one server that's good enough for him. Okay, k equals 2. Look at the two top queues. They get a lot of packets. Lambda 1 plus lambda 2 on average on an iteration. There are two of them, so they can maybe use two servers. So the top two servers should be strong enough to serve them, and so on for every k. And turns out this is, again, with the inequality being strict, this is a necessary and sufficient, obviously necessary, but also sufficient condition. What we could prove with JSON is that, again, very analogous to the old work with Tim about, factor of 2 loss in what we need in capacity, is that if you have twice as much, then a simple no-regret algorithm will take care of this. So if instead of the sum of the arrival rate is less than the sum of the top k service rates, I have this by a factor of 2 slackness in it, then no-regret algorithms selecting servers will take care of it. I'm going to give you a bit of a hint on how to prove this one, but I also will give you an example that says that, no-regret algorithms are a bit myopic, and to prove it more properly, which I will not be able to show in this talk, we also proved that if instead of no-regret learning, I somehow hope that the system will reach an equilibrium, which I don't know if it does, then we didn't need quite as much, like e minus 1 over e, which would be only a 0.6 multiplier rather than a 0.5. So there is certainly evidence that no-regret is a bit myopic, and interesting questions in my mind is improved version of learning. What do I mean, and what would help? And I guess maybe I'll end the talk on that point. So I guess I offered a little bit of a hint. And what do I want to give you with the proof here? I certainly don't want to go through all the details, But what I'm hoping to do is I'm claiming that everyone does no regret algorithms, you get this factor of 2, and that this band is tight. And what I'm hoping to do is show you how do we use the no regret property, and why is it that no regret can't do better than this? It seems like the factor of 2 is very built in to the no regret band. So our biggest mathematical tool is a elegant, but I hopefully very believable theorem in probability theory by Pimentel and Rosenthal, which is thinking about what they call a random process, which is just numbers coming at you at random, like 7, 8, 9, 2, 3, 4, 5, 7, 21, whatever, with two conditions, which I'll be very precise in a second. Sufficiently regular. It's just like some moments are banded, like it's not jumping up and down like crazy. It can go up, but it's not jumping. And has a negative drift when large. So more precisely, when the number is above some band, then in expectation, it will come down. I'm going to use this, then apparently it stays banded at all times. And I claim this is sort of believable. We say the number in expectation comes down when it's above 1,000, and it's not allowed to ever jump really high up, then it feels believable that it won't go so much above 1,000. Yeah, it will a little bit because it was only an expectation, but not so much above 1,000. It turns out to be a harder mathematical proof, and we just use it. I use it for the following potential function, where phi tau is the number of packets in the system that are h tau or older, and I add this up over all taus, and for some reason take the square root off. Obviously, if the star remains banded, then in particular, there are no very old packets in the system because, a packet old h tau really contributes tau to this phi function, namely it's h at least 1, h at least 2, h at least something, h at least tau. So, you can't have any old packets in the system. So that also means that the Qs will remain banded. And what I want to give you a hint of, or an outline of, is that, the no regret property and the factor of 2 slack will cause the negative drift. And I admit the sufficiently regular is a technical and maybe not worth going into. But I think the line about the main condition is that when the potential function is large, then it should have a negative drift. Okay, so here is what that looks like. So again, we're focusing on some age group, like say all the packets that are tau old or older, and consider what are the best servers that these things could have gone to. And I claim there are two cases. Either most of the time, the old queues that have a lot of old packets are sending to the right servers at least half the time. And because I had a factor of 2 slack, half the time is good enough, then the potential function will decrease because these guys have priority, remember, as a group. If you're tau old, your priority over everything that's not tau old. So if they keep these servers busy half the time, then because of my factor of 2 slack, they will lose packets and they will have at least this part of the potential function will decrease. Of course, this was an if they find the right servers at least half the time. If they don't find the right servers half the time, that's another option. They go someplace else. But wait, they had priority. So that means the right servers are open half of the time. And then the no regret condition helps me. They could have gone there and they could have gotten half the service. So they must be getting this much service someplace else. And this is why I'm losing the factor of 2, because I have to break it. Either they're busy half the time, cool, I got service. Or they open half the time, then the no regret condition gives me that they have good service. Because if they were open, they could have gone there. Why didn't they? If they didn't, they must be doing very well someplace else. So then I set this for a particular tau. All I have to do is add it up over all the taus. and do a little bit of arithmetic that I definitely won't do here, namely accommodate the regret error. Remember that little law of T? I'm sweeping that part under the rug. So this is the sort of outline of this factor of 2 band, which I claimed is actually tight. And it's not because of the proof, but because of examples. So I can give you an example where indeed the Qs are infinitely growing, and you only have that inequality is equal rather than unequal. So it's exactly tight. But the proof is giving you a hint that that's probably will be tight. And I guess what I want to maybe do as last step is showing you an example, not the proof of this improved theorem, but an example to give you a hint of what's going on. So here is my example. Very simple. There are 2 queues and 2 servers. One server is perfect, so always serves a packet. The other one is actually quite myopic, less than half the time. And the 2 queues arrive at a bit above half the time rate. Okay, so one version would be that they both send to the stop sync, and I claimed if they do that, they have no regret. So they both sending up there, and what that means is that, they're equal, so probably getting 50% traffic rate here, accept rate here, and this is 47, so they have no regret over there. Of course, you probably also equally see that the top server, they have linear growth because I made them arrival rates above 50% and service rate is 1. So that's the easy direction. Deviating will give them regret. They, this is only 0.47 success rate, and here was 0.5. So 0.5 is better than 0.47. So, but it turns out this is good for them. And I don't mean that it's altruistic. It's pretty clear that for this guy down here doing this, it helps the other fellow because, 10% of the time the other guy is alone. It turns out it's helping him. It's helping him. Oh, I'm not doing well in forwarding the slide. It helps him in 2 different ways. First of all, because he's handicapping himself a bit. Whenever he sends up, probably he's the older packet. So he's going to get here an even better than 50% service rate. And second of all, this guy will run out of packets. So, they both get through, everything gets through. So somehow in this case, both of them, it causes regret to do this, but yet both of them have everything perfectly serviced, so it's better for them. Now you might say, and this is really the last thing I'm going to sort of talk to you about, is that weird, no regret was a natural property. What the hell went wrong? So let me try to tell you what went wrong. Our whole notation of regret was a little bit broken, to be honest. So to be more honest, in our game, we should have put these red stars in it, in our regret condition. I should have changed the notation that utility of player I at time t, not depending on et, that is whatever they did at time t, but depend on the whole history, because it does. That's what carryover effect does. Whatever happened at time t doesn't only depend on what they do at time t, that depends on everything else. So hence the improved notation that this is the actions that all the players took from time 1 to t. And in this light of notation, this is the sort of bug of how they're thinking about it. What no regret condition says that what would have happened if everyone does whatever they did, that's the same as what I had. But here is the problematic part. Utility, what I'm switching this player to is trying this X for a second, but not changing his history. And maybe the best thing I can convince you that this is unfortunately really the condition that the algorithms achieve, or the condition we used, is to give you the 1-sentence summary of how these no-regret algorithms work. They all do something that's very well known in the AI community for learning, is explore, exploit. So what's explore, exploit? You try something, try it like once or a couple of times and see, hey, did it work for me? And if it does, you do it. If it doesn't work, you back off. But the turnout in this, going back to this example, instantaneously, this is not a good rate. It has a positive long-term effect, but not a positive instantaneous effect. And this is what this says, that utility of X is an instantaneous effect of X. Not that if you stick to it, you would have wanted the long-term effect. So the long-term would come with this notation instead. Oops, sorry. This notation instead, which of course is probably too strong. So I put a question mark there. What would have happened had I always done X? Of course, this is not learnable here, right? Because how do you know what X is? So this is too strong. But we want to go a step in this direction. And I guess maybe optimistically, I put in some more recent work in slides, but I'm going to flip through that and can, yeah, I don't guess. I want to switch the conclusion and I can go back to what the skipped part is if you're interested, but I guess it's better not to spend time on it now. So, learning is reasonable, even no regret learning is reasonable. But also, and we can get bands and can say that, with some increase of capacity, life actually works okay, especially if you're okay with a factor of 2 as your band. But also that no regret learning can actually be too myopic, as the example, this 2 queues, 2 server example clearly shows. And I guess opens up a lot of beautiful questions about can we make better assumptions? And in an alternate behavior assumption, I want 2 things. I want it, or maybe 3 things. It should be usually true in data, should imply better behavior outcomes, and of course, should be easy to actually achieve algorithmically, which of course, we'll probably need it for the making it true in data. I have some guesses as to what they are, and maybe my guesses are not so far from the classical no-regret algorithm, just sort of paying a little bit more attention to long-term outcomes, which the classical no-regret algorithms don't do. I can also end with saying that the worst case band, this E minus 1 over E, is coming from an exceptionally unstable outcome. So one can sort of hope even to say that no regret better learning algorithms will learn to do better than the best worst Nash equilibrium, because the worst Nash equilibrium is this insanely unstable solution, which is depicted on the picture here, where every Q uniformly randomizes between these options every single step, which is both silly and insanely unstable as a dynamic system. So I'm going to end here, and thanks everyone for the attention and interest, and happy to try to switch to discussions or questions.
Yeah, thank you, Dr. Tardos. So we can wait for a minute or 2 for the questions to show up, and meanwhile, like I can ask my question.
Sure.
So in the last couple of slides, we compared the no regret versus including let's say all the actions, or like history based regret, if that's the right word. I'm not sure. So has would considering a finite amount of history instead of the full history, uh, would it help the cause? Like,
Maybe,
would that be a good
maybe.
analysis? Just
I mean, there are some contexts where people did propose such algorithms. And I guess there's something called policy regret, where they have a definition that turns out not to be good enough for us. But if we look at what the algorithms do, they essentially do what you're proposing. They're just doing doubling search on how long should I experiment. So
okay.
you start with regular, say, hedge, and then they say, okay, let's try everything twice. Let's try everything 4 times. Let's try everything 8 times. And then they claim, then they have a doubling schedule, and they claim that under some conditions, which are unfortunately not true in our example, that learns a good enough strategy.
Okay.
Again, those papers do define what do they mean by, they have a definition of policy regret the same way I had a definition of regret. And turns out their definition is not strong enough to help us. But I'm virtually certain that the algorithm is. What they're doing is right. The definition somehow didn't work out. I'm not, this is again still open, and I'm certainly happy to advertise that this is an interesting question to think about.
Okay. Thank you. Yeah, we have some questions on the stream. The first question is, how does the no regret learning framework compare to traditional equilibrium concepts in game theory in terms of convergence properties?
So one thing in this talk I didn't emphasize is the error bounds. I just said sublinear, the error bound should be sublinear in the time. If you take worst case learning, which is always applicable because that's the pessimistic band, then they claim a root t error at time t, so square root of t. And that's definitely possible. So then you converge at this root t rate, or actually for n players, n times root t is the rate at the error rate at which you converge. So there is certainly a growing literature, or can you say better things than this, or can you make better statements? It started originally with two-person zero-sum games, and there's a lot of work on that still in two-person zero-sum games. Those are nice and have a lot of applications in, for example, deep learning people, adversarial, like there is this learning paradigm in which they, trying to train a deep learner to, I don't know, recognize humans in a picture. And what they do is have two learners train against each other, where one learning algorithm's job is to recognize humans in a picture, and the other learning algorithm's job is to feed these learning algorithms pictures on which he's going to mess up and not recognize the humans. And that's a two-person zero-sum game. Either you recognize it or you didn't. And so there's a lot of beautiful applications for this. The philosophy that those use at the very high level applies to every game. And there is, in fact, extensions to every game for not convergence to Nash, because as we know, that's computationally hard, but convergence to this correlated equilibrium instead. And the philosophy is easy to understand. The root T band and the error bands somehow went on worst case learning. What's worst case there? You're trying to learn, and I, as your opponent, will feed you examples to try to have you have as high regret as you possibly can. There is no game where my goal is to improve your regret. Even when we play a two-person zero-sum game, I just want to win. I totally don't care what your regret is. I just want to win. If I win all the time, but you don't have regret, fine with me, as long as I've won. So that worst case is on the opponent has the quote wrong objective function. The easiest way and the most way these people generate their proofs is if we run the usual learning algorithms, which could be gradient descent or hedge or any of these guys, they appear to have the property, or they do have the property, that after some initial time, they're mean-based, that is, your behavior at time t depends on the average value that you would have gotten over the first t times, which means that when t is reasonably high, your behavior is very stable. Like you mean for time t and mean for time t plus 1, that's almost the same. And so you're very barely changing. And so they invented these algorithms called optimistic gradient descent or optimistic whatever, which basically capitalizes on the fact that the opponent's not going to change much. So I can optimize my behavior a little bit better, given that I kind of have a decent guess of what he'll do today if he did that yesterday, probably the same thing, or at least an expectation. And those algorithms end up with a log T error band instead of a T error band, so they can get the error band like exponentially lower. It is under the assumption that both of you are playing one of these mean-based algorithms. So, or all the players in a multiplayer game. If everyone plays a mean-based algorithm, then you can do this and improve the convergence. Again, what we convergence to is correlated equilibrium in regular games. Two-person zero-sum games, nice because correlated equilibrium and regular equilibrium is the same thing on two-person zero-sum games.
Thank you. And the next question is, someone wants you to introduce the no-regret learning algorithm in detail. If you could give a little more intuition on that.
So the easiest one to tell you is this hedge. What is hedge? You look at, for all the actions you could have done, so going back to driving, because that's sort of the easy way to say, every way you could have driven to work, you would say you actually get a public service announcements every day to keep my life easy. But I'll come back to when you didn't get that, but say a full information version. So end of the morning, you actually can open your Google app and it tells you how long it would have taken you to drive on every ride. So you actually know how much it would have taken you every single time. Then I guess what it wants you to do is look at this average, what it would have taken, and always do the thing that, you know, would have been best with hindsight. Now, if I want to give you a sort of two-step mathematical thing of how to prove these things, my favorite one is a cheat algorithm, and cheat is the best way to do it. And it's completely cheaty, and maybe I should try to write because it's maybe so weird that it's a little hard to follow, but let me try to say it in English instead. I know if I were to give you ahead of time for every day, what's the best today, what you really should have done is done the best thing. But suppose you don't do that. Every day I give you the best what is done today, but instead you still do what's historically best. I just give you one extra day. I give you today. So I give you, what all the rats would be on every day. And on every day, you do not what's best today, but what would have been historically best given the history till today. It's not super hard to prove that this is literally no regret, no error band, no nothing. It satisfies the no regret property. It's a pretty simple induction proof. Now, why is this nice? Because to get this, I only gave you one extra day. So if I randomize a bit, I don't choose the best till yesterday. That turns out to be a horrible idea. But, do the best yesterday plus a bit of noise. Then it's not that hard with a bit of noise to wipe out that one day that you're missing. By which I mean, give enough noise so that the probability that you choose the same thing, no matter what the hell happens today, should be pretty damn high. And then that algorithm has the almost no regret property with the error that you unfortunately put in a bit of randomness. So this is called follow the perturbed leader. Follow the leader was an algorithm that actually studied a lot in the early days of game theory, and that just do the best, historical best until yesterday. And there are some positive statements about follow the leader, but in the worst case, follow the leader can be arbitrarily horrible. Like, I can make it so that, we playing some simple game like matching pennies. I alternate between head and tail. And as a result, you will also alternate between head and tail, but so that I win every time. every one of them, sticking to any one of the policy would have been good for you, but this alternation I induced you to do is really making me win every damn time. So, direct follow the leader is not good, but that plus a bit of noise has the no regret property, where the error is the noise, like however much noise you need to put in to make this work. That's called follow the perturbed leader. Perturbed is because we put in the noise. Maybe that's the most intuitive thing I can offer there are many versions of this, and in a very high level, they all do the same thing. Basically try to do what was best last time. They put in the noise they use, they all randomize, and the noise they use is a bit different. Different algorithm. Hedge, this is not hedge, this is follow the perturbed leader. Hedge is exponential scheme on which for where two policies have been almost equal, then choose between them 50-50, and generally as one policy was worse, exponentially decrease the probability that you will do that. So choose randomly between equals or almost equal things and use an exponential function to decay the probabilities of things that weren't good in the past. But in high level philosophy, they're all doing the same thing. Randomize between similar things and try not to play the things that were really bad in the past.
Okay. Thank you. The next question is, how easily are the players able to calculate this long-term non-regret strategy?
So I kind of gave you the strategy if it was a full information game, that is, you get all the past information. I admit it's more tricky to do this if you don't get full information. So in the packet case, you know whether your packet got rejected or not, but how do you know whether, had you sent it to a different server, what would have happened? You don't know that. On the car traffic, there is Google, so you get some full information. But if I make the assumption you know how long it took to drive on 101, but you don't know what it was in the other one because you weren't there. There is a nice mathematical trick to correct for this. It's called propensity scoring. You have to claim or pretend that the cost of what you haven't seen was maybe or zero, and the cost that you have seen was something else. The trick is that you modify the costs so that in expectation, it's exactly right. So again, your algorithm was randomized. This only works on randomized algorithms. In a randomized algorithms, for every choice, you have a probability P to choose that choice. If you say that the cost was zero if I didn't choose it because I have no clue, but if I did choose it, the cost was not the cost I saw, but the cost divided by P. So I guess it scales up the cost. Then in expectation, the cost of every choice is exactly right. Like zero plus cost divided by P is times P, the probability that you choose it, that's exactly the cost. And then I can just use the law of large numbers that, on average, this cost will actually do the right thing because the expectation was right every time. What I did, which makes the errors a little bit bigger, I increased the standard deviation of the costs are varying now more because of the dividing by P. So you must be a little bit, this pushes up the error bands, unfortunately, or makes the error bands a bit worse because there's more variance on the numbers.
Yeah, I guess this is related to off-policy evaluation and importance
Yeah,
sampling.
yeah, exactly. Same thing.
Do you have time for one more question?
Maybe one more question. I have
Yeah,
something at
just
1:10, so I eventually have to be.
okay. Okay, just the last question. When learning from historical data, it is assumed that other players behave as they did in the past. Is it possible to incorporate the case where others may change their behaviors?
Yeah, that's so actually on one of the early slides before I switched to the queuing version, we actually did this in the classical case when the iterations are all sort of new games, so no carryover effect. You have to be a little bit. What we're proposing is that in that work is that what you should do is a little bit change your learning to not be mean-based, as maybe something I just explained in answering questions, that most of these are mean-based, but make it a bit more what's naturally would be called recency biased. So it's still a mean, but don't take the mean from all the way from the beginning, but bias it towards the recent history, because people might have changed, and the recent experiences you have is more, if things might be changing, might be more reflective of what will happen tomorrow. The condition I need to make proofs out of this is that it's not, the behavior of other people is not wildly oscillating. So maybe some assumption that people change their probability behavior with some small, possibly even constant, but not 1, some probability p, not 1 all the time, and then of course the p will come into the band, or you can make p even less than constant, and then it washes away. But if it's widely oscillating behavior, of course but then somehow feels like learning is not doing anything anyhow. But if it's not widely oscillating, even though with a large population, if everyone changes their behavior with some probability, even like 1%, there will be people changing all the time, but there is enough steadiness in the system. If 99% of them is not changing every day on that day, there's enough steadiness in the system that learning can do good things in many cases. And I guess I don't know this in the queuing system. We worked it out in auction our paper is mostly about the auction application. So online advertisement auction, people might change, the priorities might change. That's fine. Again, as long as the change is happening at a low change rate, like 1% at a time, or this probability, small probability each step.
Yeah, I think this is enough. Yeah.
Well, thank you, everyone. And I guess, as much as I did actually have something in a couple of minutes, so I have to leave. If anyone from the audience wants to send me further questions, I'm certainly up for trying to answer them offline, like by email or something.
Thank you so much, Dr. Tardos.
Sure. Happy to. I hope it was useful.
Yep, definitely. The discussions and the entire picture, everything was really useful, and hopefully it was the same for the audience. Yep. Thank you again.
Thank you.
Yep. With this, we can stop the talk.
Okay.
Yes. Okay. All right, everyone. See you next week on new seminars. Bye bye.